So I assume the mic is working, right? So let's see. Okay, thank you. So okay, after several weeks already now, I guess we finally should start talking about information. So let me start with an a just what should I say, like an couple examples first. Let's say I mean, like as far as we try to describe or talk about information, maybe the first thing is like how what do you mean by information? Like anything can be information, right? Any piece of news can be considered as information, right? So, for example, like I apparently we cannot kind of like quantify. What the things like for engineer we want to do is like to quantify the information somehow. It would be difficult to quantify the value of information. For example, like if I say a piece of news, like for example, let me just make some like kind of like random example here. Let's say uh uh like let's say the president uh okay, I just make up something here. Uh will die next week, let's say. So so okay, I'm just making something, it's not a curse or something. So let's say like and maybe another thing say another let's say um the sun will rise from the east every day next week, let's say. So I can write more statements like this. The question is like, okay, which one is more valuable? That would be difficult to judge. But what engineers and computer scientists would like to consider is like, uh, which one will contain more information, or like which one we can if we consider that as a piece of news, if we want to compress it, like which one will have more content inside that? Um, I guess okay. I guess this will be too early to ask this question, but let you think about this like for the moment, and then like you, I mean, like just sink in and think of like you can write down any piece of news, and then you say, okay, which news is have more information content, which one does not have as much information content as the other one, and now as I said, like it's hard to quantify information with as like how valuable they are, but we may try to one way is I try to recompress that piece of information as much as we can, and we if we can compress it a lot, then that piece of news maybe does not have as much information as it's supposed to be. Um, but before I go into that, like let's give an kind of like another example. Let's say uh, if I consider the pi, the value of pi here, pi is equal to 5. Something like that, like pi, more or less. Of course, I can write it with infinite precision. Okay, not at all. So we can write pi in with an infinite precision, right? So now the question is like, okay, how about this one? Like, how much information for pi? So of course, it has an infinite precision, right? Does it means that we have an infinite amount of information in the value of pi there? So maybe this is a question I guess you can try to think about now. So what do you think? Like just if I say like the value of pi, um, do you think? Of course, like the question will be like, well more or less like, do you think it has an infinite amount of information or like finite amount of information? Okay. I guess I would say like finite may be okay. It depends like how you judge that. So yes, it's really depends on perspective. And so either way, like it's kind of like an okay answer. I guess it's more like um uh, in what way you're trying to think about that. But as I said, like okay, if I consider each piece of information here, like any piece of news here, anything here, if I think of like um how I'm able to uh, put this information into kind of compress that into maybe just on a hard drive or something, then of course I here I have infinite number of digits here, so therefore like I may need a infinite size of a hard drive to store the value of pi alone. But at the same time, I know there's algorithm to find that. For example, like I know that pi is equal to, I think it's 4 times like 1 - 1/3 plus 1/5 minus one, something like that. Like this I forgot what's the formula is called. Like, but you can definitely find pi like using this equation in the sense that I can write a program that with only a finite lines of code. And of course, like to compute this with infinite precision, then I will need infinite amount of time. But let's say I don't care about like a computation cost there, then that's okay. This is like something I won't get into, but like that's something like it's just good to know as long as Komogao of complexity. That it's like a you can think of it as a different perspective. So this is a perspective. I'm mathematician and computer scientist. He tried to program off try to quantify a piece of information here, like how much information in there. Using this called Gauss capacity is thinking like, um, if I give you a piece of news here, um, how much line of programming code is needed to generate this piece of news? So for pi, I can write a code of some for loop or something like probably like several lines of Python code, and I can regenerate pi like with infinite precision, right? So in that sense, the Kolmogorov complexity is not that high. But this is not the picture we'll study here though. Like this is like not something like people in electrical engineering and information theory say study. So at least like this is not the first thing they consider. Instead, like people here will consider something known as entropy. That's essentially like we're trying to uh, think of things like along the line of probability, like in a stochastic sense. So of course, like this is a kind of pi is a deterministic thing. But here, if I go back to these two pieces of information here, um, let's say I think of like not of course like if I try to compress like this thing or like I just put this words by words like into just code it into a hard drive. It doesn't have like much information here, but instead like we trying to quantify not in terms of like the wordings here because this wording like can change to different languages. Then it will be different. Like um, it probably will. It's not something we're interested in. We're interested in the semantic things here. Like what was the message underneath what we've written down in these statements here. So then if I look at like each of these statement here, let's say I say like the president will die next week. I'm also like uh the sun will rise say from the east side every day next week, let's say. Now what we should consider is like first thing, like if that things, of course like this is like a prediction, right? In both cases, I'm writing a prediction somehow. Um if this prediction doesn't come true, we'll say this piece of information is valueless. Basically it's like basically just fake news. Then that shouldn't cause any. I mean, doesn't count any information there. So it only counts when it's actually a true piece of information, right? It's like saying, okay, yeah, the person will die next week, and then like he really died next week. And also like the sun rise like every day, like from the east side next week, and it actually happened. Now, in that sense, then let's say if the person really died like next week, then I will kind of argue that the first piece of information is much should contain much more value there, or like quant. Yeah, this is my wording is not good. So we'll have more contents there because I just simply because the second sentence here we know it's going to happen anyway, or like unless something really I don't know like, but with a very high chance of probability that it will happen, right? But the next one, like even though the person is old, like at the age, like there's some chance of dying, but like still that chance is pretty slim, right? Like for next week, then the chance that for this one is really going to happen is will be pretty small. So the first thing we will argue is that like, okay, if things is like not going to happen and it actually happens, it should be more valuable. So of course, like in that sense, more valuable is not in the sense of monetary value because apparently some piece of information related to finance eventually will have more monetary value. But here we're just talking about like what's the chance of like happening. If it's less likely to happen and it eventually happen, then it have like more values. So okay, so we'll get into that. But like I hope everyone agree with that. And here I just cross out this part. Like we're not going to think about like the Kolmogorov sense anymore. We always I think along the probabilistic sense in this class. Also we ignore this pi here. So we just focus on this one. So now let's think of like another like piece of information here. So let's say I'm going to throw a dice, a dice, and I will get a 6. Let's say now think of that like how if okay not think of like this wordings here like if I'm trying to compress this wording, of course it depends on what kind of language, as I said, like I have like different kind of like a different number of bits needed to compress this. But let's say just think of this as a message here. So how many bits do you think is needed like to compress this piece of information? Or maybe like maybe this is a may not be represented very nicely. Yeah, this is along that way. Maybe I give a quote unquote like um in general, like how much information in predicting outcome of throwing a dice. So okay, my question is like try to quantify that in terms of bits. All you guys know bits, right? So this is like teach like undergrad like in both computer science and engineering, right? So bits just in terms of like binary digits, like um for example, like uh, if I have 2 bits, then yes, that would be like 3 bits, right? Because if I have 3 bits, like not more than 3 bits, basically saying that like because I have 3 bits, I can have like 8 outcomes here, right? I can store like 0, 1 to up to 7, right? So then if since I floating a dice or like throwing a dice or like tossing a dice only have like 6 outcomes, apparently I have 3 bits is sufficient, right? And also as you will see that like okay, if this is not a dice but it's like some random number, a random variable x here, but with like 8 outcomes, like 0 to 7 here, right? So if like I have the random variable, now this variable is uniform also, in the sense that the probability getting like 0 up to 7 the same, then by the same argument, like actually here, like I would say like this is like less than, this is actually like less than 3 bits here, right? Because like I only need like the first 6 values like to, or I don't know, to represent this like outcome of tossing a dice, right? So I don't even need to use a 6 and 7. Let's say if I use a 0 up to 5, I don't need to use 6 and 7. So I don't use up the entire 3 bits. So therefore, for the outcome, like for predicting the outcome of throwing a dice, it's less than 3 bits apparently. Now, if I back to here, that like I have like random variables with like outcome like 0 to 7, have like 8 outcomes here, then that would be precisely 3 bits, right? That's 3 bits, right? If this is uniform, by the way, right? Why I say if it's uniform only? Because I think of that, like if I have a random variable x, but let's say if the distribution is like I will only always have like 0 or 1 coming out, and like for 2 to 7, it just never happened. Basically, I have a distribution is like this. The distribution like this, like 0 and 1, this is like 0, 1, 2, 3, 4, 5, 6, 7, something like that. For 0 and 1, that's like the probability is 0 0.5. And for the rest, it's like all 0. Then, of course, like I don't need 3 bits to do that, right? To store this, let's say I don't call this random variable x. Let me, I call it random variable y. Also, the potential outcomes is like 0 up to 7. But let's say it only have like non-zero finite probability to get like for outcome 0 and 1, and for the rest is like just probability is 0. So okay, by the way, what's the amount of information here? Let's say now I can almost use a more technical term, say like let's say like call it the amount of information for the random variable y here. Let's say, what do you think? Like, so here I can say like this is a floating a dice, like this outcome I call it x here, that can get like 0 to 6. I know, or actually I have this one also. I already, let's say this one, like for this one, the variable x here, the amount of information for this random variable, like unless I think of like this random variable, like can generate some kind of information here, in the sense like you can think of that like uh, wh- um, I'm trying to predict x, and turns out I'm really able to predict x, then this is some kind of like information like for me to um if I let me put it again. Uh, I have this random variable x here. I, as a predictor, trying to predict the outcome of x. Um, if you think of like I am a make perfect prediction of x, then the amount of information like of x is equal to the amount of information like for me, this predictor is the same thing, right? So these two should be the same. And okay, anyway, I guess I'm digressing a little bit. I'll come back to that one later on, but let's I hope this is clear here for x and y here. So and for this dice here, if just think of the amount of information for throwing a dice is less than 3 bits, amount of random variables like from 0 to 7, like this is uniform, is 3 bits, right? Exactly 3 bits. For throwing a dice, okay, by the way, it's less than 3 bits. And the question is like, if I have a random variable y here, now also get outcome like 0 to 7 here, but only if the first two is like possible for the West is like, yes, in this case, only one bit, right? One bit is needed, right? Because, yeah, it's just one bit, right? Because I don't need to store the rest of outcome, right? I only need to do one bit. It only either give me a 0 or 1. Then I just need to one bit to store this 0 and 1 value, right? So therefore, you see, like, okay, what's going on is like the number of outcomes will, of course, like give a bound to the total amount of information. Let's say if you have some kind of like random event here that have number of outcome is n here, then as you can see, like the number of information, the amount of information for this random event cannot be more than log n, right? Because I or log to n, not to n bits, right? Because you always can use log to n bits. You can label the event outcome like from 1 to n, and definitely you can just use a log to n bits to store all the possible outcome. So therefore, like it won't be larger than log to n. But on the other hand, it's also affected by the distribution. If if that's the, as you can see, like if the distribution is more skewed, like in the sense like only some outcomes are more probable, actually some outcomes are more probable than the others, then the amount of information will decrease as well. So this is a general observation. Now actually I can even argue like this, like now I will give an actually you eventually you only need the distribution. You only need to know the distribution to quantify the the entropy or the information of that random variable. So now I can get into like more precise definition of what I like to describe. Basically, I want to quantify the amount of information of every random variables. When I have a random variables, I want to say like how much information in that random variable. So you can think of like when I say what's the amount of information of that random variable, it's essentially meaning that okay, if I follow this random, okay, if I try to um think of this random variable like like this the first two statement I'm writing it down. So and this is going to happen in the future. Now, before the random variable happen, I trying to do the prediction, and if my prediction go right, or like my prediction will always go right, I should say, and I want to say like how much value of my prediction, um, or in the sense like how okay, I think I'm making it more complicated than it should be. Um, let's see if I should step back. Um, okay, let me defer this. Let me defer my explanation. Let defer my precise definition here. But I'm saying that like I'm trying to quantify. I'm here. I'm just trying to quantify the amount of information of a random variable in the sense that like you can think of like if I'm going to um trying to store the value of the store the outcome of that random variable on average, how many bits are needed for me to store that info, store that random variable, store that outcome of the random variable. Let me repeat it again, or maybe I should write it down. So my objective is something like that. Like define random. Now I have something like pretty precise now. Consider any random variable like x. So I'm trying to do something like um kind of like some kind of information measure here. for X. So my information measure is like what I'm trying to do is like um, how to address this. How many bits needed on average to store the outcome of a of X. So this is like how I define my information measure for X, or like how do I quantify the amount of information for a random variable X. Now I can even argue the entropy. Eventually this is actually known as entropy. I'm going to give a what should I say precise proof, or like we'll give a more rigorous proof like later on. But here I'm just like hand waving. I'm trying to argue like why entropy is like with this expression here. As you think of like, okay, if I have a random variable, just think of discrete random variable. I have outcome, let's say like x1, or like maybe x, maybe just simply like 1 to n, let's say like different outcome here. 1 to n here. These are different outcomes. And I have like if I have the probability p, let's say like for this one, like for outcome one is like p1, let's say for x, I maybe like I just simply write x1 and makes sense is probably better. Like so let's say like this probability is px1, like for the first outcome is px1. So now if I try to let's say now I can go back to my prediction, that kind of like mindset. Like if I try to somehow a predictor, I know it's going to be x1, and I predict predict make the prediction that like is x1, and it's actually happened. Then I would say that the amount of information for that particular prediction will have it will contribute like this amount of information, not px1 minus of px1. So see if this will make sense to you. Maybe not immediately, but I think like it's not hard to argue for this value as well. So think of like, for example, like our example earlier, that we have the random variable like have like 8 outcomes, or like uh, the other case, I have 8 outcomes, like all of them are uniform, and also 8 outcome, but the first two is it's only the first two have like non-finite probability. In the second case, let's say like in the first case, first case, let me withdraw the first case. First case, like we have all of them, I have same probability, right? So uniform, and all of them is like will be 0.125, right? 1/8. And in that case, like you can think of like for each of this guy here, the amount of information for these guys is like log 1/8 is equal to 3 bits, right? That's how we get 3 bits, right? Or you can think of like for this one here, have probability 1/8. You can imagine that it's like if I ask like how much information is just for this particular guys, this will be like I have a uniform distribution, and the uniform distribution have the I say a uniform random variable that have, let's say I call this p here. This the probability here is p here. If I ask like how much information for this particular guy, it will be like asking like how much information for another random variable that is uniformly distributed, but the number of outcomes there will be equal to like 1 over p. For example, for here, like I have like 0.1 to 1 to 5, right? And the amount, the number of, it's hard. I'm sorry, like my doesn't articulate too well. So the number of like different outcomes here is like 1 over 0.125, this 8 here, or like 1 over p, that would be yeah, again like 8 here. And so yeah, therefore it's like just log 1 over p. Yeah. For this one, it's log 1 over p. This is not actually approximation. The argument here is approximation, but I'll show you that this is not approximation, but this is just an argument why you see it will be like this. So if I look at like x1 here, right, for the x1, maybe I hopefully like you guys see that, like for x1, if I just consider the outcome for x1, how much information will be contributing for that particular outcome will be like, maybe I write like this is better, log 1 over px1. Because you can imagine that like maybe the second example is better, because the second example I have a distribution is like this way. So this one is like 0 0.5, 0.5 like that. Now, if I ask you like how much is contributing like from this outcome here, x1 here. So you can imagine that the amount of information is contributing from this one is like log 1 over 0 0.5. It's like I'm actually have, it would be like same amount of information if I have another random variable, let's say y is uniform, but I have the number of outcome is 1 over like px1. So okay. If you don't get this part, it's okay. Actually, this is I want to give some intuition, but doesn't hurt like for our later discussion. But maybe you can go back on sometimes to think a little bit about that. It shouldn't be uh, um um and yeah, yeah, it should be something like quite natural actually. So then this is like for x1, right? Outcome x1. If x1 happen, then the affirming information is this one, right? So therefore, like in general, like of course, like x1 only happen with probability px1, right? This is like the amount of information contributed by x1. So therefore, it will be like this one, and then I need to add the other one, like x2, and x3, and so on. Right? I should be have a sum like that. So therefore, it should be just equal to sum of pxi log 1 of pxi, something like that. And this is like the entropy that's kind of like discovered by Shannon. And of course, I can put the minus sign inside, like why that's like minus px log px, something like that. Maybe I sum over xi, something, whatever. And you can also write it as an expectation, because if you see that it's really an expectation, right? Expectation of log px here. So we'll come back to that. Like, don't worry about like if you don't remember this. I mean, this doesn't. You don't remember this formula or something like that. Like this should be a formula that you will always remember. Like after this class, like you will see it many times. And as I said, like if you think about that, like this formula is very natural. Like as I said, like this is like just a weighted sum of like minus of px, and for each outcome. Oh, the negative sign is that you should consider the positive sign. Negative sign here is just 1 over px, right? So it should be log 1 over px, but you have log 1 over x is equal to minus log x, right? So it's just, oh, yeah. So and maybe a little bit of history, like it's kind of interesting. Shannon, like of course, is a great mind. Uh, this at that age, there's a even greater mind, like from Neumann. Like this is a really genius of last century, and he discussed this like to von Neumann, and he said like, okay, I have this formula. At the beginning, he want to call this like information measure or something like that. But then von Neumann told him, well, why you call this that? Like because in statistical mechanics, we have something like known as entropy as well. It is essentially the same formula with like a little bit difference here and there, like just the unit and there. And you should definitely, okay, two argument. First thing, like someone invented that before, so you definitely should use the terminology entropy. And secondly, a lot of people know, like understand like statistical mechanics. Uh, at least like for the from the engineer, especially at that time. So therefore, if you run into an argument, like people will be kind of hesitated, like to question you more. So therefore, like kind of like challenge, like kind of like accept his advice and then like call this entropy. Um. Okay, but this is just a hand waving argument here. What I'm giving, I will give a more kind of rigorous proof, like why entropy is like expressed this way. And essentially, it's like from this perspective, it's like if we consider any random variable, and just think of like the entropy is essentially like how many bits are needed on average to store the outcome of that random variable, and will be the entropy. Um, so and let's see what was more. And okay, before I trying to show this, I need to digress quite a bit. Like first thing I need to kind of like digress into is I need to talk about law of large number that I'm going to use as I mentioned last time. Um, the law of large number is something bilateral. Actually, after that, like maybe I just give a preview. Law of large number, I will talk about like some typical things, like typical sequence. Then we can show that like um, basically what I'm trying to show um, for this one here. Um, we'll also like show this like with like a forward and converse uh, uh, um, argument. So in the sense like we will first show that like we will be able to store the amount of information with like the the entropy so many bits. So by the way, like it's easier to now give the terminology, like give the symbol for the entropy. Typically, if you have a random variable x here, uh, if it's a discrete random variable, the entropy of x will be like written as a hx. Um, maybe a little bit preview for that. If the random variable is continuous, like usually we will have like a small h instead. Like this is known as the differential entropy. So essentially, like it's still the same equal to expectation of minus log px, but as you if you are aware that like if the random variable is continuous, if this is okay, this is a continuous random variable. If it's continuous, then like this won't be a sum where it will become an integral or something. So therefore, like the formula are a bit different. So therefore, like people kind of denote that like differently. So just to let people aware that okay, this is like this we are doing like the integral instead of like doing a sum here. Um, okay, as I said, okay, sorry, like for a little bit digression for this thing here. Um, so for the proof here again, like what we are going to show later on is that like we'll show that like we for forward case like we only need we can use hx bits. So hx bits forward case is saying that like the information is not more than hx bits or like it's less than hx bits. So with hx bits, we are able to find some scheme to store the outcome of X. So this is a forward. Um, and then so this is how do I say? This is the information is less than hx bits. And then we'll show that info, okay, actually less than or equal to, is bigger than equal to hx bits. In another, like this is a converse. There will also show a converse. It's showing that like if we try to compress the information like less than hx bits, then we will definitely not able to recover the message because here we're saying that we're trying to store that information, right? Store the outcome, right? So it's like some kind of compression here, doing some kind of encoding here. So when we want to get back the original message here, we need to decode, right? So if we try to compress more than possible, like if we compress more than the entropy, then we will not able to recover the original message. So okay, this is just a preview later on, but okay. So therefore, don't worry about that if you miss something now. So we'll come back to that. So, but as I said, like we will first look into law of large number, and we need that to describe something like a typical sequence, and this will give us the forward. We will try to use that to show the forward. So, and of course, like those things are useful, like especially law of large number is useful on its own. And I will give an interesting example, like just to illustrate a use of law of large number. But the law of large number is something pretty lateral. So if we talk about a random variable x here, again, like some random variable x here. So the argument is simply saying, if I pull out a sequence of x here, like let's say from this random variable here, like you can think of this as like a random source now. I just sample from this source many times. And I take an average of those outcomes. So I assume this x, of course, I have a numerical values here. The outcomes are numerical value. So I can just simply take the average. So this average will converge to the expectation of x. Actually, you can even say like this will just equal to expectation of x, almost surely equal to expectation x when n goes to infinity. So almost surely just meaning that like sometimes it won't be expectation equal to x, but that probability is like negligible, like can be randomly small. So, and this is known as the strong law of large number. Um, this is harder to show. We won't try to show this. On the other hand, we'll show a weaker form. It's known as weak law of large number. It's saying that like if I take this average here over n, if I look at how its defense kind of different from the expectation there, expectation of x, the difference here, if I ask like how far this difference is like bigger than some random number, let's say basically for any delta bigger than 0, I can always say that this probability will go to 0 as n goes to infinity. So this longer, okay, maybe this is strong law here, and this is known as the weak law, large number. So we're trying to show this weak law of large number. Um, this basically is okay. It shouldn't be too hard to show, even though like every time I need to reread that, like I'm not honestly really good at math. Like I need to come back and look at that. But it's quite easy to understand though. So for the relog a large number, like more precisely, actually, we're trying to show is something like that. Like this is equal less than, let's see, bounded by I think it's variance of x over n delta or something like that. Let me make sure. something like that actually. So therefore, as you can see, like if I have if n goes to infinity, then again this will go to zero, right? So therefore, like this is as what we desire. So we want to make sure that like this thing is not going to be I mean the FH here, the empirical, this is essentially just an empirical FH, right? So the empirical FH is not going to be uh, different much from the expectation, basically, as long as like we take this kind of like takes this n goes to infinity. Um. Okay. So okay. I guess I maybe before I prove that, like to make things more interesting, I just digress first, like to one application of LLN here. So let's think of like okay, I guess I hope this get you interested. So like let's talk about something like the Cayley criteria. Maybe I don't even need to mention this name here yet, but it's okay. So this is related to like wealth management or like betting or like gambling or like whatever like people think of that's usually many people got excited. So let's think of something like that, a scenario like this. So I have $1 here. Maybe like you are gambling with Robinhood or something. Like you can buy fractional, like any fraction of a bet. And let's say I have a bet that I can get with probability P. Let's see. I have this like one for I think it's called one for A for one bet. Let's say I have A for one bet. A for one bet. And the winning probability is P, let's say. So what does it mean is that like if I bet for $1, that's what with probability P. So something like uh I have my let's say if I make a bet here, let's say y is the outcome here, or maybe I call it r is the return here. Okay, maybe I just write like this. So I will have probability p. My outcome is like with probability p, I'll get back $8 with probability p, and with probability 1 minus p that I will get 0. So that's what does I mean. So is that clear? Yeah. So it's just I have just one kind of bet here. I'm doing just one kind of investment. Think of like the many stocks, but I just pick one stock. That stock will give, I'm do not invest in any other things else, only on this one. And I can invest any amount of dollars, but if I'm betting on $1, I will get back like $8 with probability P, and I will get nothing with probability 1 minus P. So is that clear? So now let's say I'll kind of like invest X fraction of my wealth. So for example, if I have $1, then I'm going to invest like X dollars here. Or like if I have $100, I will invest like 100X here at one time. Then now, of course, like, okay, we can think of like what's the, let's say just invest one time now. So I have 1 minus X that I didn't invest, right? This is not invest. And I will have X I invest, and I think of like the expected return, let's say, let's say like my original wealth is W0. Let's say W1 is my wealth after first investment. What's the expectation of W1? will be like, definitely I have 1 minus x, I didn't invest, right? I have 1 minus x here. And for that I invest, I will have basically probability P, I'll get back AX, right? So therefore I will have PAX, right? So does everyone agree with that? So now, okay, maybe a simple question here. When should I invest? Of course, if A is bigger, then it's better, right? A big, B big, like both cases it will be good, right? I want A and B big. If A and P big, I will invest, right? If A and P is bad, then I shouldn't invest. So when should I start to invest? Let's say first simple question here. I would say like if PA is less than some values here, I shouldn't invest at all. And PA is bigger than something, I should start to invest, right? If let me just give you that, like PA less than what, then or like more than what, I should start to invest. What is that? Just look at this one here. Oh, by the way, like X is like the fashion we invest. X is like something you can choose. Here, like we can pick X to be, yeah, actually, but I guess Sarah's answer is more or less correct, but yeah. So PX is, yeah, PA is supported. Like, yeah, of course, I make it easier. Actually, my question, I already give you the hint that you can consider PA together. Uh, as you can see, like if your, for example, like if your P is smaller but your A is bigger, then maybe you still like worth to invest as long as PA is big enough. So it's the same for the other way around also. Even like P is quite big, if A is too small, then maybe it doesn't worth it to invest also. Actually, I want to say Sarah's answer is actually already, yeah. Okay. Yeah, Richard is right. I mean, like, or you can simply say PA is bigger than 1, right? So if PA is less than 1 here, then it doesn't make any sense, right? If PA is less than 1, then I have like 1 minus, or I can write like this, right? PA minus 1, X, something like that. So you look at the PA is less than 1, this is negative here. The more you invest, the more you lose, right? So because X is the fraction of wealth you're going to invest, So you definitely should invest only when PH is bigger than 1, right? So, okay, but this is okay. This is okay. Now is a more interesting question. How much you should invest if PA is bigger than 1? Yes, but you can try to just look at here. Well, I mean, I didn't expect you to get the answer right away, but I think I um just look at the expectation here. You may get a live answer for that. When let's say PA is bigger than 1, what how okay, or let me put it another way. To maximize expected, or maybe to maximize EW1. So, okay, if I just think of it naively, I just trying to maximize my expected wealth after one investment. If PA is bigger than 1, what should I pick X? Yeah, if you look at that, it looks like it's all in, right? Yes, that's the point. So just look at this stage. It gives you a solution, it's all in. If let's say, I don't care, I just want to maximize my expected wealth in the next one, I'll just do all in. But actually, this can be a pretty bad strategy, right? And this doesn't make lots of sense. For example, your PA can be very close to 1, right? And still you're betting your entire kind of wealth like into, I mean, net worth like into that. That it doesn't seem to make any sense. So there should be a better kind of like answer for this one. So, but if you look at this one, actually, like, yeah, we should do all in, right? Because if this is bigger than 1, for example, if this is 1.1 here, or like this is a, sorry, PA minus 1 is 0.1, let's say, then if X is equal to 1, then I'll get like 1.1. It's like, yeah, but that's probably bad. Now that's how we can start trying to use like what we learned like about law of large number like earlier. So let's say we can do this investment, like most investment we can do it multiple times, right? Let's say this is like an investment is not one time, but we can invest it multiple times. No, actually, if you can invest multiple times, you don't want to do that because like here, like we, that's the point here. Actually, we're trying to maximize the expected wealth like only, but we don't count on the risk. Here, like it can be the expectation is high, but at the same time, like it can be pretty risky as well. Like there's a good chance we lose everything. Um, so okay, now let's change the setup again. Like, so not really changing the setup, but let's say if we are allowed to do repeating investment. So let's say I can do W0 at first $1, W1 at like I don't know how much, WFD and so on and so forth, right? I can do repeated investment. Every time I'm investing X there. Now what's going on is like for W1, if we think of W1, the value of W1 will be like that, right? If we invest like X amount to our X amount to that batch there, we have 1 minus X plus let's see, plus AX back, right? With probability P, we will get so much amount. Right? If we rename the bat, here 1 minus X is like we didn't invest on that. Like this one is like we get back AX, right? So this is like if we win. So if we lose, we just get 1 minus X, right? That will be like with probability 1 minus P, right? Now this will be essentially as a random variable, right? If you look at that here, this is a random variable. W1 is a random variable, and and oh, okay. By the way, I'm missing things here. This is a fraction, right? I should write this multiplied by W lot, right? I can have W2 also is like something like this. Also 1 minus X plus AX, W1, 1 minus X, W1, something like that with probability P, probably 1 minus P like this, and so on and so forth. And now if I think of like after n step here, let's say I invest n times, I look at Wn here. Wn will be essentially something like equal to, I have like let me introduce another variable for this one. Okay, let me how do I write it is better? Okay, sorry, let me change this to, I call this G instead. I call this G1, this G2, this is like the gain. So it's something like my W1 will be equal to G1 times W0, or just equal to G1, right? And W2 here is equal to G2 times W1, or equal to G2, G1, something like that. My gain is I just looking at like with a probability trans P, I will have my net worth like increased by this fashion, right? And on the other hand, with probability 1 minus P, my net worth will shrink by 1 minus X. So then after n investment here, my net worth is essentially like Gn, let's see, Gn minus 1, and so on and so on, multiply up to G1, right? Agree with that? Like this is just my net worth. Now, if I compute the log Wn, I get like log Gn plus log Gn minus 1 and so on up to log G1 here, right? Plus log G1 here. Okay, the reason I want to do a log is I want to do a sum here. As you can see, remember, okay, we have the law of large number. If we have the sum of something, if we take the average of that, okay, let's do the n of that. I know this is going to converge, right? So because you see like each of the G1, G2 is actually is IID. They all have like the same distribution here. With probability P is equal to this guy, with probability 1 minus P equal to this guy, right? And this one here will simply kind of like converge to the expectation of log G. Maybe I just simply call it G, right? It's expectation of log G, right? And what's the expectation of log G here? Is like simply with P probability that like is log 1 minus X plus AX, right? And plus 1 minus P log 1 minus x, right? And so therefore, as you can see, like I have my net worth after n investment will converge to n expectation log g. Okay, and let's see, have an exponent of this guy. Maybe I just write exp here, right? So I just like multiply n to the other side and do exponential on both ends. So I have like net worth will kind of like converge to this thing here after n investment. And of course, like if you look at that, like n is fixed and exponential is like a monotonic function, then I'll get my net worth is maximized if I try to maximize this guy, right? So if I try to maximize this, do you try to solve that? Like maybe like, so what I try to solve is like, I'm trying to maximize this way, maximize these guys with respect to, okay, maybe just ask a simple question. I have a feeling that maybe some of you already lost. So with respect to what? I should try to maximize. Yes, yes. And it should be quite simple right here. So I will take a derivative. I set it to 0, so it's like p 1 minus a minus 1x, something like, I think like take derivative of this one, I have like minus a minus 1 back, or like 1 minus a, and per say 1 minus p 1 minus x minus 1, something like. So, and you try to solve that. This is equal to 0. It should give you back. Okay, I skipped the algebra. I just, so it's give you something like ap minus 1 over m minus 1. So that you see, like, okay, if again, like your ap have to bigger than 1, otherwise x will be less than 0. Of course, that means that you shouldn't invest. And also, like, if you see that if p is less than 1, that's almost always the case, right? If it's always win, then there's no way people will have, like, but as long as p is less than 1, you should always not all in, right? If p is less than 1, you see like this is always x is less than 1 here. If p less than 1, x is less than 1 as well. So it makes sense. Like, unless, okay, this is the important lesson learned. So you should always not all in. Uh, unless you know this is like kind of cheating. I mean, you get the probability of winning is like 1. Otherwise, you should never all in. Um, and okay, any question for that? Like, this is known as the Kelly criteria, essentially. So it's something like if you do repeating, if you're allowed to do repeating bet, and the probability of betting winning is p for a for 1 bet, then your amount, the fraction of your net worth, like fraction of money you should invest in, it should be like given by this formula here, ap minus 1 over a minus 1. Yeah. So this is like kind of an application of law of large number. So now get back to a simple proof for the weak law. So essentially saying that, like, okay, for any random variable here, this is a random variable, right? The average of that random variable, empirical average, will just simply converge to the expectation. Yeah, you need to get data first. Yeah. or even though you have lots of data, I guess. Right? So let's see. So again, what we want to show is like x1 blah 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 up to xn. Now let's call this just a sum m, like let's say maybe like it's just simplify the notation a little bit. So we want to say this sum n over n. So this is the empirical average will converge to the expectation of x. So the weak law is saying that this will be less than some delta, the probability that sorry, not less than the probability that like this exceeds some delta for any delta bigger than 0 is bounded by variance of x over n delta square. That's what I'm trying to show. So what we are going to use is something known as the Chebyshev inequality. So again, this is pretty easy to show Chebyshev inequality. I don't know what order you want. Want to show this using Chebyshev inequality first, or like want me to show the Chebyshev inequality first? But basically, the Chebyshev inequality is saying that if I have some random variable y here, random variable y, the probability that like y is derived from the expectation is less than the variance of y bounded by a square, something like that. You already see like, the form is pretty close, so it seems like it's very easy to plug into that to show that. Okay. So this again, like this one is like something we try to show. This is known as the weak law of large number. That you see, we already used the law of large number, so I like to prove that. Like it won't be a difficult proof, so therefore I like to go through that. Like the way we are going to show that is I just use this Chebyshev inequality. Of course, I didn't show this here. Like I should show this as well. But maybe I will just use that first to show the weak law of large number and then come back to show the Chebyshev inequality. So for this for the weak law here, you see that like immediately, like if we try to substitute y as this guy, this should get pretty close to probably like we should immediately get the weak law. So let's try to define y maybe as something like x1 xn over n. Let's say try to define y like this. So now expectation of y is equal to this is something like this is something that I expect you guys is able to do. Like this is like the proof itself, like most likely you won't be able to recall that, like, but for something like that, like you should be able to know, okay, for example, if I have this like expectation of y should be what, because like this I can use like some just the linearity condition or the linearity property of expectation. So I can just like split that into like expectation x1, x2, and so on, like expectation xn over n here. So, but all of these are ID basically, all of them same distribution is just expectation of x. So times n over n, so it's just expectation of x here. So already we got these two parts actually. If we plug in y is equal to this guy here, then expectation of y is equal to expectation of x. So everything looks good. So actually, apparently we already have like this is less than now. It's less than what? It's less than the variance of y, right? The question now is like what's variance of y? So variance of y is equal to here like x1 over n plus x2 over n n over n, something like that way. Um, or you may, yeah, okay, let me stick to like this. So now variance of this thing here, variance itself is like, I shouldn't say it's not linear, but if you have like two independent variable, x and y, variance of x plus y is equal to variance of x plus variance of y. Um, you should be able to easily to show that because this is like variance is an expectation x plus y square minus x y. Okay, let me just quickly show the step here. So variance of x plus y is a expectation x plus y minus expectation x plus y, or maybe I should use x plus y bar here, plus y bar square, right? Something like that. Then we can should be able to expand the terms. Then you have basically we want to form something like expectation x minus x bar square plus x minus y bar square plus something. Then this something like it turns out it should be equal to 0. And so the term you have there like will have something like okay, I guess this is I will digress quite a bit. So I would just say if you don't trust that, like you just try to show it yourself. Like this should turns out to be just y, something like that. Yeah. So therefore like I can write like variance x1 over n plus variance x2 over n and so on, variance of xn over n. Now this one we should be careful of, like variant ax, like if a is a constant, so what should be this one? What's the coefficient here? I think that this is equal to variance of ax is equal to a is a constant here, should be, let's say, something times variance of x. So what should be this one here? Yes, this should be careful because I sometimes people will get confused or like mix up, like thinking, okay, this is like expectation. If your expectation ax will have like a expectation x, something like that. Yeah. This like again, like you can easily show it yourself. Like just write it out. You should get like this is a actually for this one is easier too. Maybe I will this one I will just write out the whole thing. So because you have like ax here will be what expectation. Remember like ax squared. We have like some a formula something like that, right? So then you have like this a square. You have expectation a square x square minus expectation square a. I can pull it out. I have square here x. So that got like a square expectation x square minus expectation square x, something like that. Yeah. So therefore you have a square instead of just a. So therefore, like this one here, I will have like variance 1 over n square variance x1 blah 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 multiply sorry, sum over up to like xn here. Oops. So, and again, like these are all ID, they are all the same. They should be just variant of x. So then we'll just get like variant of x over n. So therefore we substitute there into this one here. Again, will be variance of x over n a squared. So this eventually get back the weak law of large number. So, okay, so you see that the weak law of large number, we can get that immediately just from the Chebyshev inequality. But we didn't show that. And okay, to show this thing, now let's just erase it here. Oh, actually, I forgot to break like today. Okay, let's break any maybe like up okay, I'm late for this break here. So let's take a break and maybe I come back like what like for 35 or maybe yeah, yeah, it's okay, maybe 4:35, I don't know. Let's or maybe 4:40, I don't know. Yeah, anyway. So let's do again like 15 minutes back, a little bit more than 15 minutes, and like, let's come back like 4:40 sharp. Then we'll continue to prove like the Chebyshev inequality and also the yeah, we'll show that. Yeah. Okay. Continue. So just a quick review of like what we paused and what we stopped earlier is that we try to continue to prove for weak law of large number. So for the weak law of large number here, we already showed that we can just simply plug in like y equal to x1, the sum of x1 up to xn over n into the Chebyshev inequality, and you should be able to get a weak law right away. So the remaining like I like to quickly show is like the Chebyshev inequality itself. But for doing that, like I need to digress a bit further. We want to show something along like the Markov's inequality. Markov's inequality, and okay, let me. The oops. Oh, I try to flip my cheat sheet, but it doesn't do anything. So the Markov's inequality goes like this. So if I have a random variable y, where y is or maybe let's use x again. So x is like bigger than equal to 0. It's a random variable bigger than equal to 0. Then probability of x bigger equal than some b will be bounded by the expectation for x over b. So again, this will be very easy to show. So let me just quickly prove this. So let's define an indicator function like ix, something like I x bigger than equal to b. This is like some indicator function saying that like when this argument is satisfied, then it's 1, otherwise it will be 0. So 1, 0 if x is indeed bigger than b, and 0 otherwise. So then I can write x as like I x bigger than equal to b times x plus I x less than b times x, right? So this is just split into two cases, right? This is like this indicator function say, okay, like this, if x bigger than equal to b, then I will pull out this x, right? Otherwise, we pull out this x, something like this. But if I write like this, then immediately I can write like is bigger than equal to ix bigger than equal to b times b, because for this case x is bigger than equal to b, right? So therefore like x is bigger than equal to b. If I replace x by b, so this will become an inequality here, plus ix less than b times x. And or I can even simply kind of like ignore this one, right? So it's in general bigger than equal to this one. Now, if I do expectation on both sides here, this will get me expectation of x is bigger than equal to b times expectation I x bigger than equal to b here. So, but this is like indicator function. It's just counting the number of cases like x is bigger than equal to b. So therefore, it's actually just equal to the probability that x is bigger than equal to p, right? So the on average, how much can that x is bigger than equal to b per sample, that will be just equal to the probability, right? This essentially is just equal to probability. So therefore, like I have this is bigger than expectation x bigger than b times p is bigger than equal to p, then we arrange the term, we get back the Markov inequality. So, okay, guess no question for that. So we have the Markov inequality. Now we can finally show the Chebyshev inequality. So proof of Chebyshev. Probably please. So so what we're going to do is that we simply pick, as you can see again, like here, the Markov inequalities, we can apply the Markov inequality to prove like Chebyshev inequality right away. If we kind of like substitute, let's say x is equal to y minus expectation of y, something like that, or something like that. But here, like in the Markov inequality, we need x to be bigger than or equal to 0. So therefore, instead, let's try like um, uh, let x is equal to y minus expectation of y square. So in this case, this x here is bigger than or equal to 0. So we can apply the Markov inequality. So, and let's see, for this guy here, and also let's see, let me, let's pick like b is equal to a square in the Markov inequality here. So then we immediately substitute everything. We have like y minus expectation y square bigger than equal to a square is less than equal to expectation of y minus expectation y square over a square. Then we actually, you already said we immediately get back to Chebyshev inequality, because the condition that y minus expectation y square is bigger than a square is essentially the same as y minus expectation y bigger than equal to a, right? The absolute value of that is bigger than equal to a. And it's bounded by, this one is just the variance over a square, the variance of y over a square. So this is precisely the Chebyshev inequality. So okay, so that we complete the proof for the weak law of large number here. So let's move on. Now we have the law of large number, even though we didn't prove the strong law, but at least we show the weak law here. And we also, like earlier, we show one example of using the law of large number for curly criteria. Here we want to use law of large number to define something known as typical sequences, like, and eventually lead to like a forward proof of like the entropy definition, or like people actually call it the source coding theorem. So let's see. Let's consider again like any random variable here, any random variable x here. Let's say I have like I'm considering this again like as some kind of like uh, source here. So the random variable, I can pull out values from this random variables. I just samples it multiple times. I get x1, x2, and so on, like a sequence of x here. So people like sometimes call it a discrete memoryless source. So discrete, of course, like x is discrete. Memoryless is saying that like each time that we kind of like sample it independently of previous time. So therefore, like there's no memory effect here. And so now I just from any random variable I can do that. I draw a sequence here. Then this of course is a random variable here. Now do something pretty tricky here. Consider like if I pull out x1, I have like outcome x1, right? So consider x1 and consider px1 here. Honestly, I got confused at the beginning for this kind of stuff. Like it looks quite weird to me at the beginning. So note that px1 is a random variable as well. Because x1 is the outcome of the first sample, right? X1 itself is random. Like for example, this is a drawing a dice here. It's a dice here. And it can be a biased dice, right? So I can have like the P1 is not equal to P2 and so on and so on and so forth. Now X1 maybe take a value 1 here, then Px1 will be equal to P1, something like that. But maybe like X1, in the first times I fold this dice, I got not a 1, but I got a 2. I got 2, then what I'm interested in is P2 instead. So you see what I mean here? So what I'm saying is I can have a random variable px1, px2, and so on. This is a sequence of random variable as well, right? To pxn here. Now let's consider log of that. Log px1, log px2, and log pxn. And of course, they are random variables again because x1, x2, and so on are random, and these are random variables again. I'm also like the IID actually, because all x are kind of like independent and identically distributed, right? So therefore px1, pxn, px2, and so on up to pxn also like IID. And so therefore log px1 or log pxn also IID. Now then we can use law of large number, right? Law of large number imply what? Imply that like sum of log pxi I equal to 1 to n over n will converge to the expectation. Right? Now let's do a minus sign here. I'm not sure like it reminds you something. What is this? Or maybe a question. I just see if you guys are still here or what's this one? Like yes, we talk about at the beginning, right? This is the entropy, right? We argue that this is the entropy. So what we got is something like that. Like we have, okay, look at this. This is like we have something like it's converging to the entropy now, and we say that let's denote this as hx here. So it's like this is actually a constant. You think of that, like given the distribution, px here, like of course, like px itself assumed to be a deterministic thing. Like the distribution itself is deterministic, and hx is only only depend on the distribution, right? Because the definition, like it's like px log px, like sum over x, something like this, right? Once your px is defined deterministic, then hx is deterministic, right? Now, then what we have is essentially we have this one is converged to this hx here. Now we can rearrange the term. We can put the n on the other side. So I have minus n hx here is kind of like approximately equal to log px I, let's see, sum over I equal to 1 to n. Oh, wait a sec, wait a sec. Yeah, that's fine. And then if you look at log pxi though, I can put the sum into the log, then it becomes a product, right? So it's a log product I equal 1 to n pxi, right? It's approximately n. Again, it's approximately minus nhx here. Now, pxi, because each of these x's are independent, right? So therefore, like this is just equal to px as a vector, right? So think of like the probability to get this particular sequence will be just equal to the product of the probability for each of the outcome, right? So therefore, this is actually log px is equal to that. Then I just take the log to the other side. The px will converge to exponential minus nhx. So actually, this is pretty interesting if you think of that. The law of large number saying that like as long as n goes to infinity, like this will always converge, right? So it means that like if you sample it many times here, when you sample like maybe 100 or 1,000 times here, and you think of like compute the probability of that particular sequence, the probability of that getting that particular sequence is always a constant. I mean, it's always the constant equal to this guy here. Because like hx, again, hx is deterministic, right? Once you give the distribution, hx is deterministic. And so therefore, like, what we are claiming is like, if you sample independently from a random variable and sample it long enough, then if you look at the probability of that particular sequence, the probability of that sequence is always equal to all other sequences that sample from that uh, um, that I mean sample in the same way. And also like so therefore it's actually a uniform distribution. And what's more is that actually, by the way, here the log here, of course, I'm using lateral log here, but of course, I can use log base 2, right? If I use log base 2, then this will be 2 to the power something, right? Actually, this would be better. Sometimes I mean, lateral log is easier in computation. No, it's not. It's not really like this is like something different. Like it's not. That's let's see. For the steady state, I guess it's similar flavor, but like it's not exactly. But if you think of like very high level, like you can say like more or less because it's all studying like asymptotic behavior. So yeah, it's hard for me to say it now. I don't know. Yeah. So okay. Okay, but back to here. Um, what people? Okay, maybe I immediately define the typical sequence first, and then maybe go back to prove the source coding theorem, or like that the definition of entropy is like makes sense. So so basically, from our argument here, is saying that like we put out all sequences, like eventually, essentially, the probability will converge to this something like that. In a kind of like I would say uh, a maybe redundant sense, we can define something as long as a typical sequence that is a if a sequence that like the probability of x, this is a sequence I rejoin from sequence maybe x1 up to xn. The probability that is bounded by 2 to the minus n h x minus epsilon to n h x plus epsilon. So we say like any sequence like this, then this x is defined in something like, I think it's like some notation like this. So this is I look at the typical set of typical sequences. Of course, you see there's some dummy variables here like epsilon or n, whatever here. The point is like you can make this epsilon as small as you want here, right? As long as you make your n is big enough. For example, like here, if as long as we make the n big enough, if we pick any epsilon for any epsilon, we can find n for sufficiently large n. We can make like the probability that a sequence x is not typical to be arbitrarily small, right? So because we know that if we draw a sequence like long enough from this source here, that sequence that eventually will converge to the probability like 2 to minus n x, right? So therefore, like should be within this bound here. So therefore, like we can control this bound here. Okay, maybe you say we allow the bound to be like kind of like wider. Then we don't need as big an s as an n. But if we want this is too smaller, then the n will be bigger. But note that like this is very similar to those calculus argument there. Like this, I take the limit like delta epsilon, this kind of things. Like they usually like doesn't really have any real practical users here, like for the epsilon and n here. This is like just trying to make a theoretical argument. So it's like something like doing limit like df x dx is equal to a limit delta x like fx plus delta minus fx over delta, something like that. So this delta here is like more or less a dummy. We don't actually care about like what they are like in practice. Here, the same thing. We don't care about this epsilon in reality, like what they are. But the argument is like we can make this epsilon arbitrarily small. It doesn't matter. But no matter how small they are, we can always make the n big enough such that like the probability to be not typical to be as small as possible. So it's something like we draw everything like essentially or write like this. If we arbitrarily draw a sequence, the sequence to be inside this thing will be essentially equal to 1. Something like that. Um, of course, we can say, yeah, something like that. And that's the definition of typical sequences. And we can actually immediately we can ask several questions here. How many typical sequences there are? Approximately how many typical sequences? I'm not sure you can see that right away. Anyone want to try? Actually, we have sufficient information here, but like, I guess you need to have reasonably clear mind to see that. In particular, I'm not a um uh close, actually close, but almost, yeah, actually almost, yeah. So maybe I give you some hint and see. So we remember that, like, again, we are pulling from this set here, and basically when we, the argument is like this, like we have a source here, like this discrete memory source. We pull out the sequences here, and all the sequences, they are typical. Essentially, you can think like that, like roughly speaking, like all sequence I pull out here is typical, all of them typical. And also, like, remember the for all the typical sequences, they actually have the same probability. The probability is the same, almost the same. The probability will be px will be almost always approximately equal to the minus NHX. So from this, like, can you argue how many typical sequences are there? Actually, at least you can get a bound, or maybe not um, completely precisely answer. So yeah, okay. I guess like this is probably a trickier question. So because like all the sequences are typical, right? So okay, maybe let's try to do that. So think of like I have the definition of like typical sequences like this way, and I can think of like what are the probability of x is in the typical sequences here. That's very close to one, but will be bounded by one here, right? Um, and all the typical sequences have the same probability, right? So I have like px, and I can write like this, right? Basically, the probability x to be typical will be something like I sum over all the x here in the set of typical sequences here, typical set, sorry, the same, the set of typical sequences here, and the probability of this particular x here, right? So this is actually basically the probability, right? But this px here will be more or less equal to the 2 to the NHX, right? Minus NHX. So, and this will be like independent of this sum, so I can pull it out. So I have 2 to minus NHX. I sum over all this. So essentially sum over AS and X1 here. And this is just like counting the number of typical sequences, right? So therefore, this will be just equal to epsilon and X here is basically, then let me just write this is approximately even equal to 1. So we will approximately 1. So therefore, like you have like AX and X will be just equal to 2 to NHX, or like close to 2 to NHX. So the size of the typical set will be like just the number of typical sequences will be 2 to NHX. And we can make this argument more precise. For example, like this is always less than equal to 1. So then I will, and this probability is always lower bounded by like 2 to NHX plus epsilon, something like that. So then I can have like this is bounded by 2 to NHX plus epsilon. And by similar argument, I can say this is always bigger than equal to 1 minus some delta here. So then eventually you will get something like that. Like the number of typical sequences, to be more precise, would be like bounded by something like 1 minus delta 2 to the nhx minus epsilon, something like this. So, but I would say like this 1 over delta, 1 minus delta, and this epsilon is not very important. So the main intuition is like the number of typical sequences will be roughly like 2 to nhx. Each of them, this is like lateral, right? Because you think of like all of them are uniform, right? All of them have a probability of approximately 2 to the minus nhx, right? So therefore, the number of them should be simply the inverse of that, say 2 to nhx. So let's see. There are usually more things I like to talk about typical sequences. I'm not sure. But in the homework, okay, by the way, I posted the second homework assignment. So, and there's a question where I ask you to verify something is typical. That essentially just want to, want you to show that the probability of that things is bounded by this. So therefore, like it's typical. And usually I spend a bit more time on typical sequences, but I'm thinking maybe I don't need to. Oh, where you see that hx is an integer, that's oh no, that's approximation. Yeah, and also that's so epsilon or something like that. This is just some theoretical bound or something like that, or like this is an approximate, so therefore like there's no um um yeah, actually if you go to notes, as I said, like I can repeat my argument that use the bound here. Earlier, I just say like um, probability of some sequence, like pulling out from that discrete memory source is always typical. So I assume this thing here. But more precisely, like I should have kind of like more rigorously, I should kind of like set up some bound, maybe this less than equal to 1. So there's some slim chance that you get something that's not typical. And also like, so therefore like this also will be like bigger than equal to 1 minus delta. So this is less than 1, but at the same time it's very close to 1. So I want to say it's bigger than equal to some 1 minus delta or something. Delta is very small. So if I do that, like I will have so that the size of the typical set, that's the number of typical sequences, will be bounded by, as I have written here. There's no minus sign here. 1 minus delta 2 to n h x minus epsilon, something like that. Yeah. So but as I said, like don't worry too much about this epsilon and m and delta or something like this. These are like the dummy variable inside calculus. Like they are not exactly very important. The important part is really the intuition that all the sequences you pull out from that source is essentially have the same probability simply because of the law of large number. And the probability is precisely approximately 2 to the minus nhx. And so therefore that would be like inverse, so many of them is like 2 to nhx. Approximate. Of course, this is approximate, so therefore like we cannot say therefore like 2 to nhx has to be an integer or something like that. So yeah, let's see. Is there anything I'd like to talk about typical sequences? Okay, with this, I guess I can really give an argument for the forward proof for the source coding theorem. So we say this, maybe I just make a source coding theorem. People used to call that source coding theorem. Not, I guess still like people call it source coding theorem. It's something like if you have this so-called discrete memory source, it's just a random variable x here, and I'm going to see how far I can compress it, right? So then in the sense I try to create an encoder here, right? I I put a sum of sequence here, like xxn here. I encode it into some symbol y here, let's say. And from this y, I'm going to decode it back. Oh, sorry, it should be like x1. Right. So, and the thing is like, how many bits are needed to store this y here? So such that like my x can be recovered almost losslessly. I want to x1, xi, like the probability xi is not equal to xi hat to be 0, something like that. And this is like precisely will give us the definition of the entropy. And the result will be something like, as we already see, that on average, each samples will need hx bits. So therefore, like y will need n hx bit to store. So this is the final outcome here. And once we show that, then we can really argue that like so for any random variable x here, the amount of information per sample will be approximately hx bits, right? So because I for n of the samples, I will need n hx bits. So therefore, like per samples, we will need hx bits. So that indeed the average amount of information per this random variable will be hx bit. So as I said earlier, this gives us a more rigorous proof of like why entropy should be defined as like as we defined earlier. That's basically x is equal to expectational minus log xy log px. Now we are ready for a forward proof of this of the source coding theorem here. So the forward proof is saying that I can find a scheme. Mm, no, Likewise will be a different things here because for likewise the source is continuous typically, right? We're doing the Fourier transform there. We look at that. We will continue. We think of that is actually in a continuous domain. Your value is continuous. Here, like even though we talk about the source simply discrete, but things can still be pretty subtle. Yeah. So okay, yeah. For the forward proof here, we want to show that we can find a scheme. At least we can find a scheme that like if I have a source here, like I have a sequence, any sequence pull out from this source here, I would be able to find a scheme such that like we can compress this source like into n hx bits, and we can recover that losslessly. So then that we know that the amount of information per sample will not be more than hx bits, right? So that's the objective here. Okay, so our scheme will be very simple. Actually, really simple because we look at this source here. Remember that like we have this discriminant source from our argument earlier. Any sequences pulled out from this source, if the n is big enough, will be typical, right? That would be typical. That's the main thing. So, and we know how many typical sequences there are. There are only 2 to NHX typical sequences, right? Then what we can do is simply, we can label all these typical sequences, right? 1, 2, 3, 4, and so on up to 2 to NHX. Then we just look at that, okay, if the sequence we get is like the first sequence, we just store 3, right? So since I have like 2 NHX, so many typical sequences, I have 2 NHX, so many indexes. So the number of bits required to store that would be just like log 2 to the NHX, or just simply equal to NHX, right? Done. So then of course, with that labels here, we at the decoder, we also know precisely basically have the same code book as the encoder. We know, okay, this label corresponds to that particular typical sequence. So therefore, we can recover losslessly. So yeah, so therefore, like really very, very simple. That's the forward proof. Yeah. As long as this is we know typical sequences, we understand typical sequence, we know a lot of large number, then this, yeah, this is very simple. Then we need to go to the converse proof, but before I go to the converse proof, I want to introduce the conditional entropy. That's something like x plus given a condition on some y here. And the way to understand this conditional entropy will be something like, if you are given y, actually, I guess it's the best way to understand it is also like from the this kind of like compression setup here. So conditional entropy. Let's say I have some x here. I have a source here, x, discrete memory loss source. Let's say I have like both x and y I'm drawing from here. The source, I can put out some x and y here. Now I have this x here. I have an encoder again. So, but in the encoder, and also like allowed to get some y here into the encoder. And then like using both x and y, I'm trying to compress x only. So I compress it into some c here. And with some c here, at the decoder also receive the y and recover x hat, something like this. So now the question is like, how many bits per sample are needed to compress x given y. So let me just ask you a question. This, of course, this is not a quiz question here. Let me ask a quiz question here. Let's say if I have let's say like let's say I have the distribution of x. Let's say the conditional distribution is given here, like px given y. So this is essentially saying that given different y, I have a different distribution of x. Let's say I have uh, y1 here will have some one distribution like this. Let's say this is a px given y1 here. Then I can have like y2 have another distribution, px given y2 here. So if I given y1, given y1, maybe y is equal to y1. I'm thinking, should I give you a multiple choice or something? So how many bits per sample to compress x? So on average, let's say for just the case that y equal to y1, I will know that like you have p entropy of x is equal to this, right? So I can have something like, maybe I'll give you some multiple choice here. Maybe a simple y is equal to small y here. And let's see. Okay, I just give you some multiple choice here. So let's say if I have y equal to y1 here, I'm trying to compress x with this information now, like sign information now for kind of like helper information to compress x. So like this y here is input to like both the encoder and decoder here. So the intuition is like with this information, like sign helper information, I should be able to compress the x a bit more, right? So let's say like just consider the instance that like y big Y is equal to small y. So the first case like for big Y is equal to small y here. So because like each time here, for example, like this is a random variable, right? So you sample each time, right? So sometimes y will have like sample y1 or like a value y1 or sometimes get a value y2 or something like that. Like each time have a different sample. So say like when y is equal to small y, oh okay, yeah, that's good. So yes, I guess you see the point. So right. So in the sense that you when in the case when y is equal to small y, the number of bits I need to compress x should be just this, right? You can think of like in that sense, it's like the distribution now is looks like it's a different distribution, right? I have x, the distribution is convert to like a distribution p is given y, where y is like a parameter. It's like a distribution of x parameterized by some parameter y here. So therefore, when the site information is equal to y, then the number of bits required will be just like this one, right? So now I can ask the average now. So then on average, now change the question now. On average, how many bits? So now not a particular y, but like for any y, right? So then like what will be your answer this time? Yes, yes, good. So on average, then it will be just a weighted sum of this guy, right? So I will have this guy here. Actually, I can denote this one as a h big X over small y here. So then on average, the number of bits needed will be like simply hx given y, py sum over y, right? So that will be essentially this one. So because like this one is a px given y, I have a minus sign outside here, log px given y here. And then I have this multiply, I have pxy here, right? So I have a y here, okay? Actually, I have a sum over x here, sum over x, right? Log p x given y. Okay, very nice. Yeah. So, and I want to say like this thing here is essentially the definition of hx given y, the conditional entropy of x given y. That's physical meaning is like on average, how many bits per sample is needed to compress x given the size information y is available. So this is like in a compression or communication context, like coding context. But in terms of like in general, like in a probabilistic like event kind of like things will be like given two events x and y, knowing y, how much remaining information for x essentially, right? So if the remaining information is small or like close to zero, then that means that like I don't need any bits at all. If like this remaining information is huge, then I need lots of bits to compress that information, right? Lots of storage to compress that information. So that's conditional entropy. So that's the definition of conditional entropy. So or like let me rewrite this again. Maybe some page here. So conditional entropy. So it's like x given y is given by the sum over y py is like sum over x, put a minus sign here, p x given y log p x given y, and this is a I can write it as h big X given small y here. So it's like really, or like I can write this therefore is like equal to also expectation of h x given. This is like kind of like this notation pretty bad though. So this is a expectation over y. So maybe forget about that. So because this notation can be confusing. Yeah. So that's conditional entropy. And now I guess I probably have enough element for me to show the converse proof here for the source coding theorem. The converse proof is saying that, okay, if I'm going to compress the source, converse proof, source coding theorem, So what I'm going to do is okay, again, let me have the picture again. So I guess I'll use the notation in my notes here. So I have X, this is the source here, Xn coming in. Then I'm going to compress into like something like called code here. Now I label it as C. Then I'm trying to recover into Xn here. Like so, this is an encoder. This is a decoder here. Now my argument is like, if my if my if C is less than the entropy, so if C is the amount of information of C is less than the entropy, then probability of error won't go to zero, so cannot go to zero, something like that. Actually, yeah, that's fine. Yes. And but actually, I'm not going to show this one, but I show the essentially a very similar argument, similar statement. Basically, if probability of xn not equal to xn hat goes to zero, then C has to be bigger than HX, like something like HC has to be bigger than HX. The amount of information for C has to be like bigger than the amount of information of X. C. So we'll use something, okay, we'll use something known as the Fanos inequality. Again, like before I'm showing the Fanos inequality, okay, I was just say what's Fanos inequality, then like I'm going to first like show the converse proof and then go back to show the Fanos inequality. The Fanos inequality in a kind of like a rough sense would be something like the Fanos. Is that like Hxn given C over n will goes to zero if error go to zero, the probability of error go to zero. So the probability of error is defined as basically probability or probability that xn not equal to xn hat. This one go to zero. So okay, before we use Fanos to show that like the Cohen's proof. So let's look at the physical kind of get the physical meaning for that one. So C is the compressed value of C here, right? So the final is simply saying that if there's no error, if error is nothing, then given C, on average, right, per sample, like because hxn given C over n is essentially per sample, how many bits, in terms of like how many bits, like how many remaining information are in xn, right? And of course, if there's no error, xn can be, okay, C, of course, xn hat is a deterministic kind of function of C, right? We can recover xn hat like just from C alone. If there's no error, xn essentially is xn hat. So therefore, like given C alone, the given C here, then the remaining information per sample for xn should be goes to zero if there's no error. So right, so it makes lots of sense. Okay, these things alone, actually, the finals is very natural. Yeah, I hope you agree with that. So now then, huh, okay, I guess I see I still missing something. I try to do this like uh uh okay, okay, it's okay. So I have yeah, sorry, actually it seems that I still need to give out one more equation that, but this okay, it's a simple one. So I define the conditional entropy already like this, right? Now I want to say like, of course I can define joint entropy. If I think of a pair of variables as like one single variables, then I can define joint entropy as like something like pxy, this is like minus sum over xy log pxy, right? So this is joint entropy. Yes, I'm sorry, my handwriting is so bad. Yeah. But we'll come back to show this. Actually, but I forgot to mention one more thing. It's like the um, yeah, no, not at all. Like yeah, it's yeah. I try to find a table that I can write. Like I'm holding this like um yeah, my handwriting is bad already. Like it's difficult to yeah. Let's see. So okay. For joint entropy, like I can define something. This is like very large, right? This is a joint entropy. Now know that like I can for this guy I can split that into a px times py given x, right? So I have log pxy xy here. So then I will have like minus xy pxy log px minus xy pxy log py given x. Now remember this one here is just hx given y, right? Hx given big y. This is the conditional entropy. And for this one here, I note that p I have some of x and y here, both x and y here, but log px does not depend on y, right? So I can actually pull out the sum here. Okay, this is a sum over x log p x and then sum over y pxy here. But this just marginalize that. Okay, okay, let's say a quick question here, just a kind of like I would say a review of probability. What is this again? What is this value here? Yes, it marginalized to what? This was this value, sum over y, pxy. Yes, 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 yes. Yeah, this is just px, right? So this is px, right? So therefore, like this thing here is just equal to hx, right? So you see, I have hxy is equal to h. Sorry, this I have a typo here. It's a hy given x. Hy given x. So I have hxy is equal to hx plus hy given x. Okay, again, if you look at that very natural kind of formula here. So if you think of like what's the amount of information of both x and y is equal to amount of information of x added with the amount of information of y, given that we already know x, right? Very simple, very reasonable. So, but remember this equation here, we need this equation. So sorry for the digression because I forgot that I actually need this. Yeah, of course, we will revisit all this. You actually, this is like some of these things I expect you to know by heart. Like this is like some of these things I should know by heart. Like by the end of this course here, um, this something if you still remember a little bit something about this course, you should remember this kind of stuff. So I will use this. Like this is very natural thing, natural equation. Now I can really go use the finals to show the converse proof. Now the converse proof will go like this. So think of the amount of entropy of C here. I can write CF like and yes, it's the same. Yes. When I write like this, I yeah, sorry to forget to mention that hxy is equal to hyx. So this is a convention that people use just when we write hxyc is just meaning the amount of information of x, y, and c together. So this will be the same as hyxc, for example. Like it will kind of like the argument you can shuffle around. Yeah. But of course, if you have condition, it won't be. Yeah. So, but, okay. So, here I have again a per sample like HC. How much information per sample it will be? It will be kind of like close to. So now I can write it as 1 over n HC plus HXN given C. Now, why I can add this term because simply by finals right here, assume no error. By final saying that if there's no error, this term here, this thing here should goes to 0. So that's I can just arbitrarily add this. So now, but if I put these two together, then I can use this formula here, and this will be just equal to 1 over n h c m x n, right? Now I can kind of like expand that in the other way, so it's equal to h x n plus hc given xn, right? Okay, what is this? So this is a question. It's a simple question. You may go back to look at this setup here. This is how we have this xn, c, and so on, xn hat. And one thing, okay, maybe one thing I didn't emphasize enough. Here I'm asking what is HC given xn here. I didn't emphasize enough. Like we have this encoder decoder setup here, but okay, just as like you think of like you're encoding, as in your using a zip file or something like you have a document trying to compress it. That compression thing you're kind of like this program do the compression. It's deterministic, right? So every time you do the compression, you got the same outcome. So this is encoder is a deterministic function here. So essay for this decoder as well. So given this xn here, given this h, given xn here, basically C is deterministic. So so what do you think by HC given xn should be? And think of like what is hx given y. Hx given y is the amount of information remaining in x given that we know y. So, you guys thinking or like, I guess still on? Uh, Actually, no, you don't need to plug into that. Like, you just like think of like the physical meaning of these values here. Again, like the setup here is like I have some xn plug into an encoder. Encoder itself is deterministic. Some operator. So you can think of like some kind of sine function, cosine function, something like that. Right? Different input, you get different output. But this procedure is deterministic. Now the question is like, what is HC given xn? And the meaning of conditional entropy, for example, hx given y is that how much remaining information of x given that we already know y. When we say remaining information, it's like something, yes. That would be nothing, right? Because it's a deterministic. We know xn here, c is deterministic, so we know precise what is c. So therefore, this is simply zero. This is nothing. So therefore, actually, we are done, like because like this is hxn here, they are ID, right? So this would be just equal to nhx here. So it's like equal to hx plus hx. Oh, actually, I didn't show this here, but like you can show this, but you can argue this here is just nhx, right? I hope you don't have problem with that. But or you can use this rule repeatedly, use this formula repeatedly. It's hx1, hx2, for example, if you look at hx2, hx1 is equal to hx2 given x1 plus hx1, right? X2 and x1 is independent, so this should be just equal to hx2. So, okay, but we will come back to that. So at this moment, I hope you just agree with me that, right? This would be the same because h2 and x1 independent. H is given this x1 doesn't have anything. So therefore it's simply equal to x2. So therefore x2, x1 is equal to hx2 plus x1, hx1. So therefore this will be equal to nhx, something like that. So therefore I have nhx over n. So this will just give me like hx. So done, something like. And so for this game, you see that like I can actually compress. Oh, no, not this game. Like I see that like without with the L. Let's see. Wait, I want to put a bound here. I can say that. Let me put the equality sign here. I can write like this. So therefore, like I have HC is bigger than HX. Okay, it's kind of like cheating, but this is an equal sign. I can put a bound like anywhere I want. Yeah. So okay. Anyway, so let me come back to that because it's already time. Like let me come back to this. And we still need to show the Reynolds inequality, but maybe I'll repeat a little bit. Like yeah. So that like, don't worry about that if you don't catch everything. But you guys have homework. I guess you're aware of that, and please be aware also like there's late penalty for that. So don't try not to be too late. There's a slight penalty, not a lot, but like that penalty accumulate. And homework 2 is still like next week, I think. Like so, yeah. So I guess I will just stop here. I will see you guys next week. Yeah. Bye now. Yeah.